Hello everyone, in this video I will explain you how to compute and simulate linear quadratic regulator or LQR algorithm in MATLAB for non-zero set points. As always, I created a post that nicely summarizes everything that I will explain in this video. So if you don't have time to watch this video, you can simply read this post. Everything is explained here, the equations, and the MATLAB codes, and I also present the results. A link to this post is given in the description below. Let us briefly discuss the motivation for developing this lecture and this video. So, the main motivation for developing this lecture and this video come from the fact that most application-oriented tutorials available online that are addressing the problem of developing and implementing LQR algorithms are focusing on a simplified case in which the set point is a zero state or the equilibrium point of the system. However, in practice, it's rarely the case that the set point is equal to zero. For example, when we control a temperature in our room, the set point is equal to 21 Celsius. It's not equal to zero. So less attention has been dedicated to the problem of regulating the system state to non-zero set points. So the purpose of this lecture and the YouTube video is to explain how to compute and simulate a general form of the LQR algorithm that works for arbitrary set points. To explain the basic principles and ideas of the LQR algorithm, we use an example of a mass spring damper system that you can see over here. If you want to know more about this system and how to derive its state space model, you can click over here, and this link will lead you to this web page. And this web page and the video over here explain how to derive a state space model of a mass spring damper system, and moreover, this post will explain you how to simulate the response of such a system in MATLAB. The first step is to define the state space variables. We are assuming that x1 is the distance from the equilibrium point. x2 is the first derivative of x, that is, x2 is equal to the velocity. Then, using these state space variables, we can form the state space model given by the equation 2. Matrices A and B are system matrices. Input U is equal to the force applied to the system. And what is interesting about this state space model? This state space model is a linear state space model, since the differential equation is linear. With this state space model, we can associate an output equation. The output equation is given by the equation 3. The output equation defines the output variable y, and that is the variable that we observe. So in this particular scenario, we assume that only x1 is being observed. Now, I have added the output equation just for completeness. In this particular scenario, that is in the scenario of the LQR control, I will need the state feedback. I will not need an output feedback. However, I have included the output equation in order to make this model to be as complete as possible. So the goal of the set point regulation is to steer the system to desired state denoted by xd, starting from some non-zero initial state, that is, we can assume any arbitrarily assigned initial state of the system that is usually not known, and in the general case this initial state is different from xd, and we can assume a worst case scenario that there are some external disturbances acting on our dynamics. So, the control problem can be represented by the following graph. Since we can only sketch in 2 or 3 dimensions, or in this case in only 2 dimensions, I will assume that only x1 is being controlled. However, in practice and in this video, x1 and x2 will be controlled. However, for representation and for simplicity, I only assume that x1 is being controlled. So, starting from some initial condition, that is the initial position of the mass, I want to steer my system to some desired position denoted by x1d. So, properly designed controller will do something like this, where t is time and x1 is the position. So starting from some initial condition, x0, the controller should steer the position as smooth as possible to some desired position. That is, if we go back and if we analyze this graph over here, the goal can be, for example, to steer this mass from this position, for example, to some position over here. The desired position or desired states are also called set points, and they will be used interchangeably in this video. So when I say a desired state, I also mean a desired set point. So the first step is to determine the control input ud, that is this control input, with the subscript d denoting desired, that will produce the desired state or the desired set point in the steady state. Now, since xd is constant in the steady state, by substituting x by xd and u by ud in this equation, I will obtain the equation number 4, where it should be kept in mind that the first derivative of xd is 0, since xd is a constant steady state. Now, we want to solve this equation for ud. In order to uniquely solve this equation, we have to assume that the matrix B has full column rank. And here is where our controllability condition comes into the play. However, I'm not going to discuss more about controllability since this video will last for 5 hours. And I want to keep it as short as possible. Now, under the assumption that B has the full column rank, from this equation, that is from the equation 4, we can express ud. That is, we can solve equation 4 for ud, and here's the solution. So this ud, when being applied to the system, will produce in steady state the desired state. The situation looks like this. If this is time, and this is, let's say, x1 position, so starting from some initial condition, if we apply a constant ud, so this is ud, the system will probably oscillate and it will settle down in our desired state in xd. That is, in principle, we can control the system by applying the constant control input and by waiting for the system to settle down in the desired state xd. Now, what are the issues with this control scenario or with this type of a constant control input? Well, the first issue is this thing. So we might have large overshoots. And if you're considering nuclear power plant, or if you're considering some expensive device such as a pressure vessel or a temperature control system, large overshoots can create instabilities and can damage our equipment or create a catastrophic results. So we need to minimize these overshoots, right? And this is especially the case for undamped systems or for poorly damped systems. for which a damping factor is relatively low. You should be careful when you apply a constant inputs to such systems. Another issue with this type of control is that this time, the settling time, might be huge. So, the goal of the control algorithm, of the LQR control algorithm, is to produce something like this. So we want to have a much smoother response and much better convergence properties. All these facts motivate the development of the set point LQR control algorithm. The basic idea is to improve the transient system response and disturbance rejection using the LQR algorithm. So to develop the control algorithm, we introduce the error variables as follows. So x tilde is equal to the system state minus the desired state. And u tilde is equal to the current control input u minus the desired control input u that produces xd in the steady state. Now, let us substitute these expressions that can be expressed in this form in the dynamics. Here's the system dynamics. X dot is equal to ax plus bu. Now, if we plug in these variables in this equation, we will obtain the equation number 7. We can rewrite the equation number 7 as the equation number 8. Here we use the fact that the first derivative of xd is equal to 0. And let us see this term over here. This term is obviously equal to 0 because of the condition given by the equation number 4. So from equation number 4 we have derived equation number 5, so ud should satisfy both equation 4 and 5. So from equation 4 we have that this term here, or these two terms here, are equal to 0. And finally, by using these derivations, we obtain the equation number 9. So what is interesting about the equation number 9? The equation number 9 defines the error dynamics. So x tilde and u tilde are errors. This is basically the state error. How much our state deviates from the desired state, and this is the control error, telling us how much the current control input deviates from the desired control input. And once we have the error model or error dynamics, we will apply the standard LQR algorithm to this equation. In many other posts and in standard lectures and books on the LQR control is simply applied to this equation, where x is the absolute state. So the regulator problem is to steer this equation to 0, to the equilibrium point of the system. However, in practice, the set point is not equal to 0. So we need to transform the dynamics into the error form, and then we need to apply the control input and the LQR control. So having the form of the dynamics given by the equation 9, we can straightforwardly apply the LQR algorithm. So the LQR algorithm optimizes the following cost function. It's an integral from 0 to infinity of this cost function, where Q, R, and N are weighting matrices, and as I mentioned before, x tilde and u tilde are basically the errors in state and errors in input. So the matrix Q penalizes the control error, and generally speaking, larger values of Q will increase the speed of the system response. However, the trade-off is that more control energy will be spent to steer the system to the zero state. Consequently, we need to penalize the control effort, and the control effort is penalized by the matrix R. Larger values of R will generally minimize the control energy. However, this will be done at the expense of decreasing the system response, the speed of the system response. In this video, in this lecture, I will assume that n is 0. That is, that this cross-coupling between the state and the input is equal to 0. So n will be 0. Now, there are many ways to select Q and R matrices. For simplicity, I will assume that they are selected as diagonal matrices, where Q and R are some positive scalars or positive real numbers. So the solution that optimizes equation 10 under the constraint of the system dynamics is a feedback control algorithm, a state feedback control algorithm given by the equation 12. So what happens here? Having the observation or having the information about a full system state or the state error variable, remember x tilde is the error, state error, we can multiply this term by k to compute the control input error, where the matrix K is defined by this equation. Weighting matrix, B matrix, control input matrix. This term doesn't exist in our simulation, but in the general case it will be here. And S is a new matrix. So the S is the solution of the algebraic matrix Riccati equation. So this is the Riccati equation. It's a nonlinear matrix equation because we have S and S terms over here. S is a symmetric matrix. However, this equation looks very complex. Fortunately, we do not need to write our own code for solving this equation. We will use the MATLAB function LQR to compute the control matrix. You will see this later on in this video. So by substituting K, this K, in the system dynamics given by the equation 9, that is by putting here instead of U minus K times X tilde, we obtain the closed loop system dynamics. Input does not participate anymore, so this is the closed loop system dynamics. The LQR algorithm will make the matrix A minus BK to be asymptotically stable. What is asymptotic stability? Asymptotic stability means that all the eigenvalues of A minus BK are in the left half of the complex plane. From practical point of view, this means that the set point state error x tilde will asymptotically approach 0. That is, in the steady state, the system state x will become xd, since in the steady state x tilde will become 0, and x tilde is the error between x and xd. So from 15, we can also express x tilde, and we can arrive at the equation 16. And equation 16 is also important for simulating the system response. Here now we have eliminated x tilde, and we have represented the equation 15 only in the terms of x, right, of the original state, right, the state of the original system, and we have a term here, xd, right, and this can act as a constant input when we simulate the system. Also, we can express the control input given by the equation 12, by the equation 17. This is how the control input looks like. So the control input takes UD, that's pre-computed, a set point value, set point control input. It subtracts x minus xd and multiplies the results by k and subtracts from UD. So we now proceed with defining the system in MATLAB and with simulations. First, we define the system parameters. M is the mass, Kd is damping, and spring constant is equal to 10. Then we define the system matrices A, B, C, and D. and we use the function SS to define the system state space model. So here's the system state space model: matrix A, matrix B, matrix C, and matrix D. The next step is to define the desired state, or to define the set point value. So we want to steer our system to the position 3 and velocity should be 0. The next step, of course, is to compute the desired control input. And the desired control input is given by the equation number 5. So this is the equation number 5. Then we simulate the system response for the computed UD. To simulate the system response, we need to set the initial condition. We set the initial condition to be equal to some random value, random position, and random velocity, and we define the final simulation time. And let us simulate our system. Here is the simulation code. We execute this, and the result will pop up. So here's our result. The black line represents the position, and the red line represents the velocity. So we start from some position, let's say equal to 0.5, and with velocity close to 2. And here we apply a constant control input signal. So we apply a pre-computed constant control signal given by this line of code, and if we click on UD, so UD will be 30. And if we go back and analyze these graphs, we will see that our state, our position settles at 3. That's perfect. And that our velocity settles down at 0, approximately 0. So you might think, okay, controller works perfectly, I don't need to do anything else. However, observe these overshoots. We have a significant amount of overshooting, and we would like to minimize these overshoots. Furthermore, we would like to increase the convergence speed, that is, to decrease the settling time of such an algorithm. So let's do that by applying the LQR algorithm. So to apply the LQR algorithm, I need to select the weighting matrices. I assume Q and R, in this case, as 10 and 0.1. They're diagonal matrices, right? R will be a scalar, obviously, since we only have a single control input, and I assume a 0n. And then I use the MATLAB function LQR to simulate, actually not to simulate, to compute the control gain K, to compute the matrix as the solution of the Riccati equation, and E will give me the eigenvalues of the closed loop system. I specify the input parameters. They are the system dynamics, that is the system state space model, the weighting matrices Q, R, and N is equal to 0. So if you execute these lines of code, we will get our K. So let's see our K. Here it is. Here's the K matrix. Let's see the eigenvalues. You can also compute the eigenvalues by calling the MATLAB function eigen. So here's the eigenvalues. Perfect. The system is asymptotically stable. We have some complex poles. However, we cannot avoid them. And let's compare these eigenvalues with an open loop eigenvalues. So here are the open loop eigenvalues. They're closer to the imaginary axis. They're more on the right compared to the closed loop eigenvalues. So the controller is doing something, right? The controller is shifting basically the eigenvalues from minus 0.25 to approximately minus 0.72. So 3 times we have decreased the real parts of the eigenvalues. So that is promising. So the next step is to simulate the closed loop system. We need to compute the closed loop system matrix, and we are basically simulating this equation where xd is the desired state, and this is our closed loop matrix. So this will be new A matrix, and this will be new B matrix in our simulations. So we specify A closed loop and B closed loop, that is, this matrix is equal to minus A closed loop. And we specify D as 0 and C is 1 over 0, although we don't need C. And we simply define the state space model calling the function SS. So let's do that. So here is our new closed loop system. And the next step is to define the control inputs for such a system. If you analyze this case, the control inputs will be equal to xd, and they will be constant. So this will be a step signal. More precisely, this will be a matrix in our simulations where the column of actually the first row of this matrix will be x desired 1, and the second row of this matrix will be x desired 2 for the duration of the time interval. And this is what I define here, right? So this is now our step signal vector. We can execute it, or we can visualize it like this. So the first row will be 3, 3, 3, 3, and the second row will be 0, 0, 0. And finally, we call the MATLAB function LSIM to generate the response. And the final step is to compare the trajectories of the original system that is controlled by a single step signal with the closed loop LQR system. Now let's do that. And here are our results. So again, the black line represents the position when a steady state constant control input is applied, and the magenta line represents the trajectory of the LQR algorithm. We can obviously see great advantages of the LQR algorithm. We can observe that the overshoots are eliminated and the convergence speed is increased. So the settling time here is 5 seconds, and originally the settling time was approximately 20 seconds. So 4 times we have decreased the settling time, and we have significantly decreased the overshoot. Same thing happens with velocity. We can see that velocity is not oscillating anymore, and the response is much smoother. So this is a proof of principle of the LQR control, and these simulation results clearly explain great advantages of the LQR control. However, in order to apply the LQR control, you need to precisely know the system model, right? This is one of the disadvantages, because in practice, system model will often contain uncertainties, model uncertainties. And another drawback is that in this algorithm we don't have an integral gain. We don't have an integral gain, and the integral gain might the lack of integral gain in the case when we have model uncertainties might produce steady state errors. So we need to somehow include the integral gain in the control algorithm, and this will be the topic of our next video and of our next post. Okay, that would be the end. I hope that you like this video. If you like this video, please subscribe or support my channel. Thank you very much and have a nice day.